Okay, folks, good afternoon. The sign-up sheet is here. Don't forget to sign your name. We are going to continue our discussion about current mode control. We started the discussion last time, so the idea is to measure the inductor current. All of our converters have at least one inductor, so there's an inductor current in all of them. And then make a bunch of decisions based on that inductor current, in a sense that you're kind of forcing the inductor current to follow a particular pattern. Now, where is that pattern coming from? It could be an external signal. For instance, you're trying to emulate a source of current. Or, in case you're trying to, and that's usually the case, in case you're trying to regulate the output voltage, that pattern comes from the output of your voltage compensation network. We discussed at least three methods of doing current mode control. The most common one is peak current mode control, and there is valley current mode control, and there is average current mode control. We also discussed that there is a little bit of a stability problem associated with peak current mode control, and that is when the duty cycle is greater than 0.5, the system gets a little bit chaotic. There is a simple solution for that, and that is actually adding some external ramp to our reference signal, or actually subtracting some external ramp to our external signal, to our reference. There was a little bit of a math discussion behind that, how to select the slope of that external ramp. And then we also started some discussions about a small signal modeling for current mode control. The major assumption to remember that we made at the very beginning of this small signal modeler approach was we assume that the inductor current is exactly following its reference, or to be more accurate, you should say the pole current is exactly following the reference. So we ended up with a model like this, like a small signal model that kind of relates all the perturbations that we may or may not have in the system, such as the input perturbations, input voltage perturbations, the reference perturbations. There is no duty cycle here because duty cycle turns out to be an internal signal now. And we had a few observations. One of them is, at least as long as the Bach converter is concerned, you observe a little bit of a negative input impedance in the small signal fashion. And we kind of explained why that is. Also, again, as long as the Bach converter is concerned, you can argue that current mode control reduces the order of your system from a second order system to a first order system, because it kind of eliminates the dynamics of the inductor. Now, before we go any further, first of all, are there any questions? Okay. So before we go any further, let's take a look at some simulations to become a little bit better at this current mode control. So this is my classic Bach topology. It is converting 48 volts as the input voltage to 12, for instance. My input voltage is kept constant. Load resistance is kept constant at 5. And down here, I have implemented the current mode controller. We haven't talked about the compensation network design. We haven't designed this box yet. And I'm going to kind of bypass this box and actually externally command the inductor current, right? So just say follow 2 amperes or follow 5 amperes or something like that. So this is like an external, source or reference for the inductor current. Initially it is 3 amperes, then it jumps to 6 amperes at the middle of the simulation. Then this is the latch that actually current mode control works based upon. It's a set and reset kind of a latch. At the beginning of the cycle, you set it. That means you have to turn the switch on. And then when the result of the comparison between your reference and the real inductor current value actually changes, then you have to reset or turn the switch off, basically. So if we have a clock that determines my switching frequency, also I'm implementing some external ramp over here or you can just use this sawtooth waveform to actually create that external ramp and then subtract it from the reference. Now, in order to show the instability, what I do is first I basically simulate the system with no external ramp. So the external ramp is basically 0. And my inductor current is supposed to follow 3 amperes at the beginning and then 6 amperes towards the end. So we get an error. The error is basically because the system is becoming chaotic. We can actually take a look at it. So remember, initially the inductor current was supposed to follow 3 amperes. The output was, this is a buck converter, so the average value of the inductor current is the output voltage. So output voltage is hovering around, for instance, 14 volts. And because it's less than half of the input voltage, which is 48, the duty cycle is less than 0.5. So for now, we don't really have a stability problem. Everything is normal. You can observe that the duty cycle is less than 0.5. Everything is good. But as soon as I ask the inductor current to follow 6 amperes now, or double its value, or in other words, our output voltage is supposed to be around, for instance, 20 something, close to 30, you can actually observe some chaotic behavior. So you can see the inductor current is all over the place. Even in this phase, actually, we are not under a steady state condition. This is like the inductor is on, the switch is on for the entire period. Then it is off the next period. So again, on again and off again. So you can see the system is a little bit acting strange. The simulation even stopped because I had so many zero crossing in the math behind, and it doesn't look good. So now let's take a look at how we can solve the problem by adding this external ramp. Okay, so now I'm adding some external ramp, or subtracting some external ramp from the reference, and now let's run it again. Okay, so now we didn't get the error. Everything looks good. Before everything looks good, and even after the change, everything looks good. So the chaotic or the instability problem can be easily solved by involving some sort of an external ramp. To make it more clear, let me show you actually this signal. So here I'm actually plotting 3 signals. The yellow one is the reference for the inductor current, which was 3 initially. The kind of purple one is when I subtract the external ramp from the reference, and the blue one is actually the inductor current. So we turn the switch on, it ramps up, it crosses this point, and then the switch is turned off, and the inductor current ramps down. And everything looks good now, and when the duty cycle is greater than 0.5. So you can see the duty cycle is greater than 0.5. So I'm going to post this on Blackboard. If you want to mess around with it, play around with it, go ahead and do so. And also I have a compensation network that we are going to design today. And again, look at the simulation one more time in case you want to close the loop and basically regulate the output voltage. Because right now the output voltage is not regulated. You can see I commanded the inductor current to increase, therefore the output voltage increased, the second trace down there. All right. So this was to show you a demo of this chaotic behavior. Let's go back to our small signal modeling and effort. So we ended up with this, and we can actually further simplify it or make it closer to a canonical model. That's what I'm going to do now. So I'm going to actually play around with some of these parameters. For instance, For instance, I labeled R1 to be negative Vn over I1. Okay. Now, as it turns out, this is, maybe I can do it this way. Let me start with this. Let's say input power under steady state conditions is the same as the output power. So Vn over I1, Vn times I1, which is the input power to the buck converter, is the same as the output power. Okay. And instead of output power, the output voltage, I just write it as D times the input voltage. Okay. So technically, you end up with this. D squared Vn squared, just Vn over R, or Vn over I1 is R over D squared. Or you can argue that this is the buck converter. Vn over I1 kind of represents the reflected load resistance to the primary side. This like a transformer. The turns ratio is D. So once this resistor impedance is being reflected to the primary side, there's a D squared involved. All right. So I can argue that R1 is negative R over D squared. All right. So that is like our first kind of simplification thing. The other thing is we have Vp, like over here, I have Vp, which is the pole voltage under DC circumstances, over Vn, the DC value of the input voltage. So let's see if we can simplify this one. Remember, this is particularly for the buck converter. Let me also write the word buck up here. And the pole voltage in the buck converter is the same as the output voltage. So we are looking at the output voltage over Vn, which is basically D. All right. The other term that we have is Iref, which is the DC value of the reference for the pole current divided by Vn. So let's take a look at this. Okay, remember again, this is the buck converter, and the reference for the pole current is the same as the reference for the inductor current, and the DC value of the inductor current and the DC value of the load current are the same. So this is nothing but the load current over Vn. Okay, and the load current is V out over R. So we are looking at, and again, V out over Vn is D, so we are looking at D over R. Okay. So I can actually go ahead and redraw this with these new observations that I have made as this is Vn perturbed. Then I have D times Iref. And then I have another dependent source of current, which is d over r times Vp. And then I have Iref Okay, so and again remember this is the buck converter. And our control input is actually Iref basically. Okay, now what I can do is we have Vp, a small signal perturbations of Vp appearing over here, but maybe I can look at the secondary side and see what this Vp is representing. Okay, so let's do that. So basically this is Vp. Perturbations in the pole voltage, small signal perturbations in the pole voltage. Assuming that we are kind of walking to a frequency domain instead of a time domain and using impedances, I can say Vp is basically the impedance that I see on the right-hand side of my equivalent circuit model, which is an L placed in series with the capacitor that is in parallel with the resistor. So Vp is basically the voltage drop across this inductor plus the output voltage. Okay. And therefore, if I have d over r times Vp perturbed, maybe I can break it down into two terms. The first term is d over r times L times S times Iref perturbed. And the second term is d over r times V out perturbed. All right. So that block of, current source that I have up here, I can break it down into two sources of current, and then, so these two basically. And then combine the ones that are proportional with Iref with each other, and then write down the final equivalent model. And remember, since S is the Laplace character, since S is appearing in our model, that means everything is in the frequency domain. So this is like the Laplace transformation of the perturbations in the reference current. Okay, so this is on the left-hand side, and on the right-hand side, nothing has changed, basically. Okay? So this is kind of our final equivalent circuit model in terms of a small signal analysis of the current mode control. And then we can actually derive our small signal transfer functions. For instance, similar to the way that we were doing for the voltage mode control, I can look at my control to output transfer function. So if you remember, when you were looking at voltage mode control, this transfer function was shown by GVD. D as our control signal, because in voltage mode control, D's are actually control input. But here, D is not actually in our model at all, so I'm not going to... I'm just going to call it, I'm just going to call it C as control. We call it G sub VC. The V is output voltage, basically. C is actually control, which is IREF. So again, remember, this particular one that I'm about to write is only holding for the buck converter. So this is basically highlighting how the output voltage is perturbed if I perturb the reference. While the other perturbations are zero. For instance, V in is kept constant. All right. So if V in is constant or zero, everything that I have on the left-hand side of my model is zero or shorted. So technically, I just have to look at the right-hand side over here and see how my IREF is influencing my V out, which is basically that impedance that I have, which is the R in parallel, this resistor in parallel with this capacitor. All right, so these two impedances in parallel with each other. So again, as we expected, it's a first order model. Now keep that in mind that we had that very simple or simplification assumption that the pole current and the reference are exactly the same. That's why we end up with a first order model. The other transfer function is similar to before, GVG, or audio susceptibility, okay? Or line to output transfer function. Now here, since line is line and output is the same output, so still we are using GVG as our symbol for this particular transfer function. Okay, so again, this is for the buck converter. So we do not perturb anything but the input voltage, meaning that the reference is not perturbed. If the reference is not perturbed, therefore this current source is zero. Therefore the output voltage is zero. Therefore this transfer function is basically zero. Okay? So what does this mean? First of all, it's a good thing that it is zero. So technically we are saying that under this ideal assumption that we made, the perturbations in the input voltage do not appear in the output voltage, which is great, basically. So no matter what happens to our input, our output voltage doesn't see those changes, basically. So I would write it as a perfect line regulation. Okay. So the disturbances in the input voltage do not influence the output voltage, since the inductor current only depends on the reference, okay? Nothing with the input voltage. Now remember, this is true because of the assumption that we made, and that was the pole current is almost the same as the reference. But in a practical case, this transfer function is not absolutely zero, but it's very, very small. Or in dBs, it's in very like negative 60 dBs or something like that. So actually, it's a good thing. And actually, we can see that. I can actually run some simulations, and we can observe if this transfer function is really close to zero or not. So let's actually do it. Yes, we have a question.
So can't we use this kind of control method in something like solar panels kind of converter, where the input is...
You could, although in a solar, okay, remember this is a buck converter. In a solar application, you're usually using a boost converter. If you're using a boost converter in a solar application, you are trying to control the current that you're drawing from the source, which is your solar panel. So you are using this for that, but not because we have a perfect line regulation, because this only holds for this buck converter. And we don't use that buck for those applications. All right, any other questions? Okay, so let's take a look at this. Let's try to verify if GVG using CMC, by the way, I should add CMC here. That means we are looking at current mode control transfer functions. If this buck under CMC it has a GVG that is almost zero. So what I can do is I'm going to perturb the input voltage. Let's say my input voltage is not exactly 48 anymore. It is 48 as its DC value plus like 4 volts of fluctuations at 100 hertz, something like this. And then let's keep our inductor current constant. So I'm not going to have this a step change at all. Just keep it constant and then run. So right now I am perturbing the input voltage, and ideally I do not expect to see any perturbations in the output voltage. So let's take a look. And you can see it's almost constant, okay? So you can see there is a little bit of perturbation that our model was not able to predict, but if you neglect that, we are almost doing very well. And then you can compare this with a simulation model that we had earlier, which was voltage mode controlled buck. So let's look at this buck converter over here. So my input voltage is perturbed, same voltage, same converter, and I'm, let's say, keeping the duty cycle constant at 25%. And now you can see that, yes, well, by the way, I'm changing the load. Let me keep the load constant. Okay, so you can see that both these simulations that I ran are actually open loop. I haven't closed the loop yet. In one of them, the reference for the inductor current was constant. In the other one, the duty cycle is kept constant. As you can see, in the voltage mode control case, since I'm perturbing the input voltage, those perturbations are actually appearing in the output voltage with the ratio of D, which is 25%. Whereas in the current mode control, it did not actually appear, or almost did not appear. So this is one of the advantages of current mode control. You actually have a very, very low or small audio susceptibility, which is great.
How would the small signal model be like in no load condition?
No load condition. Usually you are not supposed to have a no load in a power converter, because then your converter will not even function. So your question is, if we eliminate the load, what happens? All right, if you eliminate the load, so you are, okay, let's say quantitatively you are saying that
Very small load, very small load.
very small load. So if you have a very small load, your converter is going to go to DCM to begin with. So everything that we have said is not holding anymore because it's DCM. But remember, you expect your converter to consume some load, some power, because otherwise it doesn't make sense. You're saying that my inductor current, which is my load current, should be 2 amperes, and you don't even have a load. So where is this current going to go? It's going to charge your output capacitor. So your output capacitor is going to get charged and charged and charged until you get, if this is a buck converter, it is going to get to 48. And then you're in DCM. Actually, we can do it, and you can see what happens. Okay, let's see. Let's have a very, very small load. For instance, 5,000 ohms. Okay. Almost open circuit. And then I'm forcing the inductor current to be 3 amps. So you can see on average my output voltage is almost 48, which is the input voltage. System is kind of in DCM. It's kind of chaotic, and basically I don't have any inductor current at all, basically. Something like that. But usually you don't expect your converter to be functioning anyway, because you're having a converter because you have a load which consumes power. Otherwise, there's no point of having a converter. All right, any other questions? Okay. So this was all about the buck topology, and I'm going to kind of generalize it to other topologies, for instance, the boost topology. So let's take a look at the boost. So first, let's generalize it. So using the findings that I have for the buck topology, I'm going to generalize to the single pole double through switch. And let's say I have a current okay. So using the logic that we are familiar with now, for instance, you are doing peak current mode control, there is a reference available to you, for instance, 2 amps or 5 amps or whatever, and we are switching on and off in a sense that IP is following IREF. And that logic is in this box that I have labeled as CMC, current mode controller. Okay, which turns the switch on and off. Okay, so this is equal to, in terms of a small signal, okay, so in the Bach model, we had negative Vn over I1. Vn is nothing but in the general case, V throw 1 minus V throw 2. And then I1 is basically I throw number 1, and there's a negative sign there too. So this is the value of your resistance. Then we had a dependent source of current. Which was, let me see what it was. In the Bach model, it was I think it was D times IRF, but D in a Bach converter is V out over V in. V out is VP, V in is VT1 minus VT2, so this is basically VP divided by V throw 1 minus V throw 2. Okay, and then we had another dependent current source, and the value was D over R, or IREF over V in basically. So IREF is IREF, V in is VT1 minus VT2. So let me write it in this way. Times V pole perturbed. Okay, and on the right hand side we have IREF. And IREF is our control input. Okay, P is the pole, which is basically this point over here. And obviously right after the pole we have the inductor, so we can actually draw the inductor here too. Okay, something like this. Okay, so this is a generalized kind of a current mode control model for a single pole double throw switch. So in case you have a homework assignment that I'm asking you to use this, like for the boost converter developed all these transfer functions or something like this, I'm expecting you to do this. Identify the single pole double throw switch there, take it out, replace it with this, and then go ahead and solve the model. Now, okay, I feel like I'm missing a page here. One of my pages is missing here. Did I fall anything? Okay, let me see. 1, 2, 3, 3.5, 5. Okay, this is this page over here. All right, so to practice this model, I'm going to actually apply this for the boost converter, okay? So apply okay. So all we have to do is like say, okay, what is VT1 minus VT2 under steady state conditions for the boost converter? What is IT1 for the boost converter? You know, things like that. So I'm just going to make some notes down here, then apply them to the model. So remember, the boost converter is something like this. Okay? So this is throw 1, throw 2. So for instance, you can argue that VT1 minus VT2 is nothing but the DC value of the output voltage. IT1 which is this current is nothing but the negative of the load current basically. Okay. VP on average, remember these are all the results of a DC analysis. On average, there is no DC voltage drop on the inductor, so VP and VN are the same. Okay? So, so once you plug in all these numbers that you want, this is what you're going to get. So let me just write them down here first. So I have a resistor which was a negative of VT1 minus VT2 over IT1. Okay, so this would be a negative of VT1 minus VT2 is V out. IT1 is negative V out over R. So this is nothing but just the resistance of R. Okay, then I have a current source down up here, this guy over here, which is proportional with Iref. Let's take a look. Okay, so we just said that VP is Vn, VT1 minus VT2 is V out, and this is the reverse of the voltage transfer ratio. So V out over Vn is 1 over 1 minus D, so Vn over V out is 1 minus D times Iref. Okay. And then we have this second source of current. So let's take a look at this one. Okay. Well, Iref is Iref. We can't really do anything about it. But VT1 minus VT2 was Vn. Okay. Wait a minute. That was not Iref. That was VP, right? Yeah, this is VP over here. So let's write it over here. Okay. Now we somehow got, yes,
VT1 minus VT2 is V
V out. Good point. Okay, thank you. So let's take a look at this one. We are trying to see what maybe VP represents. So looking at the right-hand side of our model, in the boost converter, VP is the voltage drop across the inductor plus the input voltage, right? So technically, let me write it over here. So instead of VP, I'm writing what I have as the input voltage plus, again, we are kind of switching from time domain to frequency domain, plus the voltage drop across the inductor, which is the impedance of the inductor times IP. Okay, something like this. And so I can kind of break it down into two terms. One of them is times V in perturbed plus, and remember IP perturbed and IREF perturbed are the same because we are doing current mode control, so we are looking at IREF over V out times L times S times I ref. Okay, something like this. And then we have some source of current over here proportional with I ref. And then we have another one here. We have one here. We have one here. We just add them together when we are actually forming the final small signal model. So let me actually add them up over here. So now I'm adding 1 minus D, oops, times IREF perturb plus the second term that I got from that, the second, source of current, dependent source of current, which is IREF over V out times L times S times IREF perturbed. So I factor out IREF. Okay, let me write it first and discuss where it came from. Okay, so I'm trying to substitute IREF over V out. Okay, so already down here maybe. Let me write it this way. IREF. Okay. IREF is the reference for the pole current. Remember, the pole current is always flowing from left to right. At the same time, in the boost converter, it's kind of opposing the source current. So I can say it is 1 over V out times negative I in. Or instead of the input current, I would say it's equivalent to the input power divided by the input voltage. Or the input power and the output power are the same. So I can write it this form. or the output power is V out squared over R divided by Vn. All right. So in the end, this is V negative V out over Vn times R, the resistance. Okay. So that's why instead of, wait a minute, 1 over V out. No, V out over Vn. Yeah, that's correct. Okay. Yeah, so far we are doing good. So what is V out over Vn in the boost converter? 1 over 1 minus D. Okay. So that's where this thing came from. Okay. There's a negative sign there too. Okay, so I kind of did this. Is there anything else that we haven't done? Vn times.
So the 1 minus D should be in parentheses then?
What do you mean in parentheses?
Up next to the blue one, the 1 minus D minus L.
Yeah, they're just subtracted from each other, yeah. So this is 1 minus D minus.
Sorry, that was dumb.
Okay, and then one last thing to do, and that is, okay, it's getting a little bit confusing, but I'm just manipulating some math to make it closer to a canonical form. But anyway, one last thing to do is, instead of Iref over V out, I can write minus 1 over 1 minus D times R, for the same reason that the very last line that you have on the screen is telling you Iref over V out is minus 1 over 1 minus D times R, and I have another Iref over V out, so I can actually replace it with that one as well. All right, so once you have all this math involved, and then in the end you are trying to kind of simplify the original model that we have. So you're trying to actually now plug in all these parameters that you have found in this model. So this is what it is going to look like. So we are looking at the boost. So I'm going to write it over here to emphasize that. So we are starting with the throws on the left-hand side, and even before the throws, in the boost converter, we have the load and the output capacitor. So now I have the throws. So we argued that we have a resistor. And in a general case, this resistor is negative VT1 minus VT2 over IT1. We kind of realize that VT1 minus VT2 divided by IT1 with a negative sign is nothing but the output resistance. So I'm just going to draw another output resistance there. Okay. Then we have a dependent source of current. Then we have another term added to it. I'm just going to write the overall results. Vp over Vt1 minus, which is 1 minus D times Iref. And then we have another term that is added to Iref, which is this Iref over V out over Ls. So I'm just going to write the whole thing. Oh, by the way, this is also the same thing. Okay. Times d prime. Remember, d prime is 1 minus d. Okay. So all I did was I'm adding this term with this term, and then I'm factoring out 1 minus d as d prime, basically. All right, then in the end we had another dependent source of current, which is this guy, and then this ended up with this expression over here, and this is going to be negative Vn perturbed divided by d prime r. I just labeled 1 minus d to be d prime. Then on the right hand side we still have the same stuff. Okay, something like this. So if you are interested in finding Bine-Sharp transfer functions for the boost converter, you should actually now use the small signal model that we have on the screen. Yes.
Is the second R in negative? Is
The second R negative? No, actually, it is not. This is the difference with the buck converter. In the buck converter, it was negative. Here,
second negative?
so there is a negative sign here. There is another negative sign here. They kind of cancel each other out. Okay. Okay. Any other questions? Okay. So this was for the buck converter. This is for the boost converter. Now, if you open up, for instance, the power electronics book by Dr. Erickson and Dr. Maximovich, you're going to see like a table representing all of these. So I'm going to actually introduce that table over here, which holds buck, boost, and buck boost topologies. They call it a two-port equivalent circuit. Okay. For current mode control. So this is the equivalent circuit model. Then I'm going to introduce the parameters in the table. They call this function f1 times I ref perturbed then they call this function, or this is like a gain of G1. V out perturbed. And then on the output side, they almost have a similar structure. G2 V in perturbed, F2 of S, I ref perturbed, and another resistor. Which is labeled R2, and then finally our capacitor and resistor. So this is like the canonical representation of the buck boost and buck boost topologies, and then they have this table over here as well. For instance, if you remember, for the buck topology, R1 was negative R over D squared. For the boost that we just developed a few minutes ago, on the input side, there is no resistance, so it's actually like an open circuit, so like infinity. And for the buck boost, we haven't done it. Maybe this could be a homework assignment, but I haven't decided yet. The resistance is negative D prime times R over D squared. What about F1 of S? For the buck converter, it is D times 1 plus S times inductor value over the resistance value. For the boost converter, it is 1, and for the buck boost, it is D times D prime R. All right. What about gain of G1? It is D over R. For the boost on the right hand, on the input side, we have nothing. And for the buck boost, it is negative D over R. What about G2? For the buck, we had nothing. For boost, we have this term over here, basically, which is, and if you flip the polarity of the current, the direction of the current, it is going to be 1 over D prime R. And here we have negative D squared over D prime R. And F2, for buck we had 1, for boost is D prime over 1 minus SL over D prime squared R, which is something we found a few minutes ago, which is basically this term over here. And for the buck boost, it is negative D prime times 1 minus SDL over D prime squared over R. All right, so this is this. And finally, R2, the resistance that appears on the load side. For the buck converter, we had nothing. We had no resistance. For the boost, we just had R. For buck boost, we have R over D. Okay. So this is like a canonical form. This table appears on page 453 of the book, and 453 used to be the course number for this class, so it's a little bit of ironic thing. But anyway, just one note. The buck boost that book basically discusses is the one that V out over V in is negative D over 1 minus D. So remember, this last row that I have is under the assumption that your voltage gain is basically negative. All right. Any questions so far? So this was basically some circuits 1 tricks and some small signal modeling tricks to be able to use our generalized model for a single pole double throw switch that is controlled under current mode control technique, to use that and develop this model. Then beyond this model, you can actually go ahead and develop some transfer functions, for instance, control to output or audio susceptibility and things like that. Before we actually get to the transfer functions, I just want to mention that there is a more accurate way of, so this was the simplified version of controlling or modeling the current mode control technique. There is a more accurate method in which, for instance, audio susceptibility does not turn out to be 0 for the buck converter. Okay. We are not going to go through the details of that model, but I just thought it may not be a bad idea for you guys to become familiar with it. All right. So that model, so let me write it over here, more accurate model. Okay. So remember, in our simplified model, we assume that the inductor current and the reference are exactly the same. In the more accurate model, they don't make this assumption, okay? So technically what they do is they start from this very basic structure or logic behind current mode control, that this is your reference, this is the external ramp, and this is the inductor current. Okay, so there are some geometrical equations holding, basically governing this logic, and they kind of perturb those equations. Now, I'm not going to perturb those equations. This is like 3 pages of equations. I'm just going to write the results. Okay, so the results are, so there is some math involved, and the results are here. So technically, you end up with, again, D, the duty cycle appears in our model. D is some gain of F sub M times Iref perturbed minus IL perturbed minus some times minus some gain times V in perturbed minus some other gain times V out perturbed. Okay, so this is a more accurate model, and they usually draw it, but before I draw it, let me introduce these gains of Fm and blah blah blah. So Fm is always 1 over T is the switching period, M sub A is this auxiliary ramp. Okay, and Fg and Fv are dependent on the topology that you are working with. So if you have, for instance, the buck converter, Fg is d squared times T times 2L, and Fv is negative 1 minus 2d times t over 2L. Okay? So these are the gains. Now if you're dealing with the boost topology, and this is 2d minus 1 times t over 2L. And this is d prime squared times t over 2L. And finally, the buck boost. This is d squared t over 2L, and this is negative d prime squared t over 2 over L. Again, this is that buck boost that we haven't really analyzed in this class, and that is V out over V in is negative d over 1 minus d. All right. So a lot of times when you open a small signal model paper, you see a diagram like this, which actually this diagram is like a circuit equivalent of that equation that I have up here. So if you want to consider this equation and draw an equivalent circuit model for it, you're looking at something like this. This is D, the output goes to the converter or to the small signal model. And then we have the perturbations in the input voltage influencing that. Also, the perturbations in the output voltage influencing that, as well as the perturbations in the reference as well as the inductor current. Okay, something like this. And then they draw the rest of the converter around this thing. So if you open up a paper and see something like this, it comes from this more accurate model. And by the way, this is not the only version of this accurate model. There's probably 3 or 4 different versions. I'm just introducing the simplest one possible. All right, I don't think we have time today. We have our spring break next week, and then the week after that, once we come back, we are going to look at some of the small signal models that we have developed for the buck converter. We're going to plot them and then design a controller and then go back to the simulation file to basically see where this transfer function comes from, and then look at some of the closed loop behavior or characteristics of the current mode control technique. Do we have any questions? All right, so see you guys after the break.